Hi everyone, welcome to the video presentation of the material that we missed due to our shortened class on Friday before break. Just to bring you up to speed, it's Monday morning. We've had about 6 inches of snow here in the York area last night, yesterday afternoon, and all the local schools opened on a 2-hour delay, but now that the sun's come out, things are in pretty good shape. So I hope you're enjoying your break. And I hope I can quickly get us through the material that we missed relating to examples with integrated rate laws and one little bit of material that we have. So if you recall, what we did on the Friday before break, just at the tail end of class and the time that we had, was develop a set of rate laws, a new version of rate laws that relate concentration to time. These are called the integrated rate laws because calculus is needed to solve the two different forms of rate law that we had previously seen, the average form and then the instantaneous form. Because the average form has a delta concentration over delta t, that's where the calculus comes into play, making that delta become in the limit of a very, very small change of time. And that introduces the derivative, and thus the integration is necessary to solve for concentration. So we could solve an integrated rate law for any order of reaction, but the three most common orders, as we've been saying, are 0, first, and second order. And these are the integrated rate laws then for the three most common orders, as we've said. For a 0 order, concentration depends directly on the initial concentration, the rate constant, and time. But for a first order reaction, it's the ln of the concentration of reactants that depends on the ln of the original concentration of the reactants, the rate constant, and time. And for a second order, it's the reciprocal of concentration that depends directly or linearly on the reciprocal of the original concentration, the rate constant, and time. In these form, remember, all three of these have that y equals mx plus b form, and we looked at the graphical considerations, how these all look like a straight line, and thus from a graph of concentration data versus time, we can infer what the order of the reaction is, as well as solve for the rate constant of the reaction. Now, the rate constant's really the key, and we see that it's in all three of these equations, right? That the rate constant is the slope of those three graphs. But rate constant's really an abstract concept. Even after many, many times of working with reactions and hearing what their rate constants are, we might still not understand, if we were told the rate constant of a reaction, that it's a fast or slow reaction. So chemists have developed an alternative that really is just a convenience that's called the half-life of a reaction. And so the half-life, as its name might sound painfully obvious, the half-life of any reaction is the time required to consume 1/2 of the initial concentration of reactants. All right. And in other words, if you've consumed 1/2, then at this T1/2, this is our symbol for half-life, T1/2, at T1/2, the amount of concentration that you have left is still 1/2 of what it initially was. It's key to think this way about how much is left, because if I didn't stress it last class, all three of these equations are describing how much of a chemical remains at the given time of interest that we have here, not how much is used, right? And those are kind of related perspectives. But the equations that we have are always how much remains, okay? So at the half-life, half of our original amount is used, but also half is left. Thus, we could substitute this into any one of these three equations up here and determine that the half-life time for a 0 order reaction would be equal to the initial concentration divided by 2 and K. For a first order reaction, the half-life time is equal to the ln of 2 divided by K. And for a second order reaction, the half-life time is 1 over K and the initial concentration. Right. It's interesting to note that there's no dependence on concentration here in the first order. Actually, this is pretty similar to what happens in the units of the rate constant, right? Look at the dependence. We have a sort of a 1 minus n, n being the order, dependence. 1, 0, -1, dependence on concentration. How the half-life depends on the concentration, that is. Okay? So this half-life is a convenient thing in that it allows us to now say, oh, instead of a reaction has a rate constant that is 0.00257 molar per second. We have no idea what that means. That might mean, oh, this reaction has a half-life of 23 minutes. Okay, that's not too bad, right? 23 minutes to use up half of what we started with. So this reaction's not, going to take forever. It might be something we could do in a lab period, for example. Versus a reaction that we're told has a half-life of, 8 hours or several days or even months or years. Some very, very, very slow reactions exist. Okay. All right. Now that we've introduced the half-life concept, let's start to work some examples, and we can use half-life and the integrated rate laws that we have already developed over here. Okay, so I'm just going to work through a series of examples. These were the ones that I'd wanted to be able to do last Friday. Okay, so first example, the half-life of a zero-order reaction was 17.2 minutes when the initial concentration of reactants was 0.42 molar. Okay. How much of the reactants remain after 25 minutes of reaction? Well, to answer this question, how much remains after 25 minutes of reaction? We were introduced to the equation to solve for that last class, the zero-order rate law right here. But the zero-order rate law depends on K, the rate constant. So what we have to do in this case is it's almost an inconvenience that we were given the half-life. Our first step to solve this problem is going to be to use the half-life to find the rate constant. Then we can use the rate constant to find the concentration that remains in the integrated rate law. Okay? So we are told, key information here, that this is a zero-order reaction. Right? So for the zero-order reaction, the half-life is equal to the initial concentration divided by 2K. So we need to manipulate this to solve for K, the rate constant. That would be the initial concentration divided by 2 and the half-life, or 0.42 molar divided by 2 and 17.2 minutes, which is 0.0122. This would be molar times reciprocal minutes. It's okay to go ahead and use minutes in our time for this one because our other time is 25 minutes. So the two times are in the same unit set, so we don't have to worry about transferring both over to seconds, for example. Right. Now we can go ahead and solve the integrated rate law. The amount of our reactant that will remain will be equal to the initial amount minus KT. So the 0.42 molar minus 0.0122 molar reciprocal minutes times 25 minutes. That will allow the minutes to cancel out. And we have simply 0.1 0.115 or 0.12 molar left over. Okay. One of the things that I like to just emphasize when we're doing kinetics problems is we often get a hint, or we have the ability to predict what the answer might be before we do the calculation, or at least to predict a range, a reasonable range for our answer. Right? For example, this problem here started with a 0.42 molar concentration. So if we're asking how much is left, well, it has to be less than 0.42 molar, right? And it has to be more than 0. All right, that's going to define a boundary. But actually, we could be a little more specific than that, because we've passed, at 25 minutes, we've passed at least one half-life of the reaction. So that first half-life would bring this from 0.42 down to 0.21. So we know that our answer has to be between 0.21 and 0, actually. And so that really makes this make a lot of sense to us, in other words. Okay? So I really encourage you to think about your answer whenever you solve a kinetics problem. Okay? All right, let's stick with this same reaction here. We can follow up with one other question here. Because there's lots of different ways that seemingly similar questions are asked when it comes to these integrated rate laws. So for this next one, how long, now we're going to solve for time, how long will it take to consume 90% of the reactants in this reaction? So how long is it going to take to use up 90% of our chemicals that we started with? The key to this problem is the language. As I said just a couple minutes ago, all of the integrated rate laws are written from the perspective of how much chemical remains at the time of interest. But look at the language here. This is how long is it going to take to consume or use up. So we have to sort of, translate that in our head. When 90% is used, that implies that 10% remains, right? It's just subtraction from 100 here. Or in other words, we would take 0.1 times our initial 0.42 molar, and we have 0.042 molar. That is the concentration at whatever time it is we're interested. We'll use that to solve for time then in our integrated rate law. Same integrated rate law, now we're solving for a different piece. Now we're interested in the time. So we would put our final concentration, 0.042, over here on the left, our initial concentration, 0.42 molar on the right, minus then our rate constant, 0.122. All these have their units, but the units are going to work out. So we would, in this case, go ahead and subtract the 0.42 over to the left. And when we divide by the rate constant t, we should end up with 31 minutes in this case. 31 minutes. Okay. Again, we should think about, does this make sense, this answer, right? Well, one half-life of this reaction, same one we just worked with, one half-life is 17 minutes. For a zero-order reaction, 2 half-lives will bring you to 0. You'll have nothing left. Okay? So 34 minutes, everything is gone in this reaction. This is 31 minutes, so we're less than that. Okay, that's good. We can't predict more time than it'll take to consume everything. All right. And 90%, so we're pretty close to that 34%, or 34 minutes, sorry. Okay. All right, let's look at some of the other orders of reactions. The set that I have for us to look at today, we'll look at all 3 orders, so you'll see the different formats all at work, algebraically at least, if that's helpful. Okay, let's do this next one here. 2N2O5 produce 2 moles of N2O4 plus O2. Concentration versus time data was collected for this reaction. A graph of ln of N2O5 versus T was linear and fitted by the equation y equals negative 6.93 times 10 to the negative 3 x minus 2.303. Okay. So that sort of preface to any questions actually is going to give us some important information about this problem. All right. So we need to pay attention to some of the key words that are used in this. But here are the questions that we have. I've got 3 or 4 for us to do here. What was the initial concentration of the N2O5? Okay. Second question, how long will it take to reach only 0.020 molar N2O5 remaining? Okay. Let's do those 2 first, and then I'll throw in a couple other questions as well. Okay. So where do we get started with this problem? Well, as I said, a lot of it has to do in this preface, right? The key here is that the ln versus t graph was linear. That tells us that this reaction is first order, right? And then in the first order integrated rate law, ln of concentration equals negative kT plus ln of the initial concentration, although we saw it flipped in order the other way, ln minus kT, right? But I'm doing that to show us that this is the initial concentration, or related to it. So that's how we're going to get the first answer. And then this negative k, here we see negative slope, negative x. This is your k, that's your rate constant. That's going to be important to answering any other questions related to this. Okay. So given the connections here, the ln of our initial concentration is equal to negative 2.303. So our initial concentration would be E to the negative 2.303, which works out to be 0.100 molar. So we now know our original or initial concentration of our reactants. So now we can tackle the second question because we have both the initial amount and we now have the rate constant for this reaction as well. So how long will it take to reach 0.2 molar? So again, this is going to be solved with an integrated rate law. First order, ln of x equals ln of initial concentration minus kT. Of course, I'm using x here, just the generic placeholder, but all this would be actually the N2O5s. Okay? So we're looking for time here. So the ln of 0.020, that's our final concentration, equals the ln of 0.1 minus, then our rate constant is 6.93 times 10 to the minus 3. Technically, its units are reciprocal seconds. I would assume the graph was in seconds, but whatever the time units are, we're going to have to be the same. Okay. So to solve this, we would subtract the ln of 0.1 over to this left side here. and that gives, and then we would divide by the negative 6.93 times 10 to the minus 3. Okay. And then our time should end up being, in this case, 232. And again, that's probably seconds, although I didn't actually give us, a specific time unit there. Okay. All right. Very similar to the problem that we just did for a zero-order reaction, but now for a first-order one. The only real difference is we have to take the natural logarithms of these amounts before we go ahead and combine them. Okay. Let's follow up with another one here. How much N2O5 remains after 5.00 minutes? This is a good one to follow up right after the previous one. 232 seconds, right? Every minute is 60 seconds, so 4 minutes would be about 240 seconds. So this gives us a ballpark for this next answer, right? At almost 4 minutes, then, we're down to 0.02, okay? So now we're asking about at 5 minutes. So the concentration would have to come even further down, right? So again, narrowing down the range for our answer is what I'm trying to do here. At 5 minutes, I expect the answer to be less than 0.02, but still a positive amount. It still has to be greater than 0. Okay. So we'll solve this one. ln of the concentration of N2O5 equals the ln of the original or initial concentration of N2O5 minus kT. So we can plug in the ln of our initial, that's 0.1, minus 6.93 times 10 to the negative 3. Now here's where our units would have to match. If we're assuming that we've been working in seconds to this point, our 5 minutes needs to be put in 300 seconds. Okay, so I apologize that I didn't clearly specify seconds earlier here. Okay. So when I do all the math on the right side here, I end up with negative 4.382. And a lot of times people think they're done when they, have a mathematical setup like this and they've done all the algebra and they get to a number, we think we're done. But given what I just said a second ago, this answer doesn't make any sense. Our concentration of N2O5 can't be negative 4.382 molar. But our sentence that we're looking at here, right? An equation is a sentence in the English language. Our sentence doesn't say that this is the concentration of N2O5. It says this is the logarithm of the concentration of N2O5. So we need to sort of undo that logarithm by taking the natural exponent, e, of both sides. Sort of like we had to do to find the original concentration as well, right? It said ln of the concentration equaled that negative 2.303. So now when we do e to the negative 4.382, we come up with 0.013 molar. That answer now makes a lot more sense. It is less than the 0.02 molar that we encountered at almost 4 minutes. So the concentration has gone down a little bit further from that point. Okay? Excuse me while I bend over to pick up my marker cap here. All right. Okay, I have one more example with this first order reaction here. And this is a great one that makes us really change perspectives and think not just about the reactants, but how do we bring in questions about products as well? Let me rewrite my reaction here. It was 2N2O5 to produce 2N2O4 plus an O2, because I want to see that reaction for this next problem here. So what concentration of O2 has been produced, okay, after 5 minutes? All right, so we just answered the question, how much reactant N2O5 remains after 5 minutes, but now we're curious, Well, how much of the products have been made, which is a more realistic question in a lot of chemical laboratories. You make something is what you're trying to do with your reactions. So, how long does it take to make a certain amount of the product, or how much can you make in a given amount of time during your work day? Those are good kinetics questions that we can answer with these integrated rate laws. Okay? So the key to this problem is that the amount of O2 made depends on the amount of N2O5 used, which in turn depends on the amount of N2O5 left, okay, and the initial amount, right? So I've just laid out sort of the steps that it takes to solve this problem. When we're asked about a product, okay, we have to reframe the question, right? The amount of oxygen that's made. I don't have an integrated rate law that's going to tell me how much oxygen there is at any point in time. So I have to totally rethink this problem. But the stoichiometry, right? We learned how to do stoichiometry last semester. So the amount of oxygen that gets made depends on how much of the reactant gets consumed, all right? How much of the reactant gets moved from this pile over here to this pile. But we take into account the coefficients, in this case 2 to 1, right? Then the amount of N2O5 that gets used, that's not what we get out of the integrated rate law either. The integrated rate law gives us how much N2O5 is left at any given time. So what we have to do first is use the amount of N2O5 that we started with and the amount that are left to figure out the amount that is used. So this would be the initial amount of N2O5 minus the final amount of N2O5. That's not the way we usually do our deltas, right? We usually do final minus initial. But in kinetics, we have to do initial minus final to get a positive sign for our answer, okay? So we had 0.1 initially minus our 0.013. So we've used 0.087 molar in this case. Okay. Now that's the amount of N2O5 used. Now we're ready to go ahead and just do some real simple stoichiometry. 0.087 molar N2O5. Now we're used to treating the coefficients as moles. However, we can do that here. 1 mole of oxygen is produced for every 2 moles of N2O5. Now those units might not look like they make sense for us, but what's really happening here is molar is moles per liter. So the mole part of N2O5 is canceling out, and the moles of N2O5 are being replaced by moles of oxygen, and you'll still end up with moles per liter. So it's quite nice that the coefficients actually are a stand-in for molarity calculations, conversions as well. Okay, so 0.087 divided by 2, with the rounding, we end up with 0.044 molar oxygen that would be formed after our 5 minutes of reaction there. Okay, so again, whenever you're asked a question about a reactant, you have to reframe the question. Think about how the reactant connects to the products. First, it's always going to be the amount of product made depends on the amount of reactant used. The amount of reactant used depends on the amount of reactant that you started with and how much is left after the amount of time that you're interested in. Okay. All right, one more set. This time we'll shift over to a second order reaction. All right, new reaction for us, obviously if it's a different order. two chlorine monoxides, two ClOs, decompose to produce chlorine and oxygen, Cl2 plus O2. Okay. This second order reaction has a half-life of 14.6 milliseconds when the initial ClO concentration is 6.2 times 10 to the minus 4 molar, okay, at 25 degrees Celsius. Okay. This is also a subtle part that we'll address the Wednesday after break. We'll talk a little about how temperature affects reaction rate and controls the rate constants. So really, half-life and rate constants, they all are temperature dependent. And most technically speaking, we should always know what that temperature is. Okay. All right. Again, I'll have a couple of follow-up questions. So this is just kind of the preface information to a series of questions. First, what is this reaction's rate constant? So what is the reaction's rate constant? Second question, what percentage of ClO remains, okay, after 0.500 seconds? Okay. Then I'll have a third question, but we'll process these two first. Okay. So here again, just like the last problem gave us information about the graph, right? And we had to infer the rate constant from the graph and the initial one. Well, here we're told the initial concentration, but we're not told the rate constant. And that's the key to solving all of the integrated rate law problems. So we're going to have to find it from the half-life. For a zero-order reaction, the half-life is 1 over rate constant and initial concentration. So the rate constant here would be 1 divided by T1 half and the initial concentration of chlorine monoxide. Or 1 divided by 14.6 milliseconds. So we might go ahead and put that into 0.0146 seconds. And then the concentration, 6.2 times 10 to the minus 4 molar. So our rate constant is 1.1 times 10 to the positive 5 reciprocal molar reciprocal seconds. Okay. All right. If you hadn't converted your time into seconds, you'd have two issues right now. One, your units would need to reflect milliseconds. So your answer would be off by 3 powers of 10. It'd be 3 powers of 10 smaller. That's okay. But then in your next problem, here the time is given in seconds. You'd have to reconcile those two times then. Okay, so you always want to make sure you're paying attention to these units of time. Okay. Now the second question asks, what's the percentage of ClO? Our integrated rate laws, again, don't present the information in that format. So this is just not a trick, right? But it's just saying, hey, solve the problem and then reconfigure the answer into this language, so to speak. Okay? But the problem is solved by solving for the concentration of ClO at this given time. Now this is a second order integrated rate law. So the 1 over concentration of ClO equals 1 over the initial concentration of ClO plus KT. So we would have 1 over the initial concentration, 6.2 times 10 to the minus 4 molar. Okay. Plus then, we just found the rate constant, 1.1 times 10 to the 5th reciprocal molar reciprocal seconds. Now multiplied by this half second, 0.50 seconds. So the seconds are gone, and our two units then are 1 over molar, so you see they can add. So this is going to, again, give us 1 over concentration. Just like a few minutes ago, we had ln of concentration. So 1 over the concentration ends up being 5.68 times 10 to the 4th. Okay, reciprocal molar. And again, that's, way out of the range of what could be possible as the answer. So what we have to do is take the reciprocal of both sides, essentially, raise the whole thing to the -1 power, and what we come up with is a ClO concentration of 1.8 times 10 to the -5 molar. Okay, that makes a lot more sense given that we started with only 6.2 times 10 to the -4. All right, so now we're down to a smaller amount. All right, we've also passed several half-lives. Okay, so we could work that part out. But the second order half-life is a little bit tricky in that it's only valid for that first half-life period. And then at the end of that first half-life, 14.6 milliseconds, we have a sort of a different starting concentration for the next period. And so it's going to elongate the half-life. So the successive half-lives get longer and longer. Okay. All right. Now, that's our concentration. But the last thing we have to do is put this into a percentage form. I even almost forgot to do that. A percentage would, just be, okay, this is the amount left divided by the amount that we started with. So 1.8 times 10 to the -5 divided by 6.2 times 10 to the -4. Then you multiply that by 100%. You get 2.8% of the ClO remains. Okay. So percentage is, just one thing compared to the initial value. Okay. All right. Let's do one other question with this. We can wrap this up. Another time question. At what time does 10% of the initial ClO remain? Okay. At what time does 10% of the initial ClO quantity remain? Okay. So now we have to apply this percentage, and it is, look at the language, it is remaining. Earlier we had 90% used, right? 10% left. Now we are asking about just the 10% left. So we could take 0.1, or 10%, times our initial, 6.2 times 10 to the -4, means that 6.2 times 10 to the -5 molar is the concentration of ClO. Now we go to our second order integrated rate law. 1 over the concentration of ClO equals 1 over the initial concentration of ClO plus Kt. And we're going to just substitute 1 over 6.2 times 10 to the -5 over here on the left equals 1 over 6.2 times 10 to the -4, our initial concentration on the right, plus our rate constant that we found, 1.1 times 10 to the 5th. And then T is our unknown. Okay. So when we go to set about here, we would solve for what these two numbers are, right? Subtract the initial one to the left side, and then divide by the rate constant. I come up with a time of 0.132 seconds, or 132 milliseconds. Wouldn't really matter. We weren't told to use one particular unit, but maybe because the original time was in milliseconds there, it would be nice to go ahead and use milliseconds as our answer here. Okay? All right, so I hope I've written clearly enough that you can see all this information, and I've verbalized it, I think, as well, so you should be able to copy it all down into your notes. These are the examples that you would use to help you do your homework. In ALEX, you're going to have several problems relating to these integrated rate laws and Half-Life. Okay? So this video should be a pretty good setup for most of your homework for this chapter. Again, having watched this video, my expectation is you do this before the Monday that we return for break, March 11th. And then we do not have lecture that morning. Instead, we'll just gather for a lab right here in the lab space at 11 o'clock. And we're going to do our kinetics, our first kinetics experiment, in which we'll try to determine the rate law of a reaction. Okay? So if you have any questions over the break after looking at the video and these examples, feel free to email me. I should be in email contact most of the time. It might take me half a day or a day to get back to you, depending on traveling and stuff with my family. But again, I appreciate that you take some time to do this over the break so that we don't have to have that first Monday morning class at 10 o'clock. And I'll see you all for lab on the 11th. Enjoy the rest of your break. Be productive, but also at the same time have a good time. All right? Take care, and I'll see you guys soon.